So let me summarize what I did. So some summary. So we see that there is a parameterization of irreducible representations. So one can denote the set of irreducible representations of a symmetric group by the set of Young diagrams with n boxes. So we write it as follows. Pi lambda is an irreducible representation with label lambda. Lambda is a Young diagram with n boxes. And next we have a character table. And this character table is denoted as follows. Here lambda is again Young diagrams. Rho is also Young diagrams, or a partition. And by definition, this quantity is the value, is the trace of the operator which corresponds to any element G, where G has cycle structure rho. So it belongs to the conjugacy class, which is labeled by rho. And then we have the master formula, the Frobenius formula. Which says the following. The power sum symmetric functions indexed by rho can be expanded into Schur symmetric functions, and the coefficients of this expansion are precisely the character value. So the sum is Young diagrams with n boxes. So this is the key result. And it is the source of essentially all information, all that we can extract about, all that we know about the character tables. As a corollary, we see that this quantity can be computed in principle as a scalar product in the algebra of symmetric functions between these two symmetric functions, this one and this one. And next I defined the characteristic map. Denoted as follows, which maps central functions or class functions. It's denoted maybe as follows. This is a linear isomorphism with the nth homogeneous component in the algebra of symmetric functions. And it is uniquely determined by the relation that the image of the characteristic function on the class multiplied by this quantity is the power sum symmetric function. So this is characterization. Next, I recall the Jacobi-Trudi formula. Trudi, sorry, is it correct? Trudi, which says that the Schur symmetric function can be written as a determinant expressed in terms of H functions. And this means it follows that the character, irreducible character, can be obtained as an induced character written in this way, where I am using this notation for the product of class functions, which is determined by induction. And I recall the notation that this is the trivial one-dimensional character, the symmetric group, which takes constant values 1. And from this, we can see that our irreducible representation can be written formally as a virtual representation. This means formal linear combination of true characters of such a type. The sum is of permutations in the symmetric group K, where K is the length of lambda, or maybe some greater number, greater, does not matter. The sign, and next we take the induced representation from a certain Young subgroup, which is of such a type. So, with the understanding that if some of these numbers is negative, then the result is 0, no contribution. And if it is equal to 0, it's dropped and induced by the trivial one-dimensional representation. Well, so this is some reminder. And what next? Next, I want to discuss some natural operations on the dual space. So in the collection of irreducible representations, the symmetric group. So very simple operations. First one is dualization, meaning the passage to dual representation. In general, if you have a representation of a finite group, we can form the dual space to its space, and we get some representation which is realized in this dual space. It is the dual representation. And so in general, for a finite group G and some representation G, we have the dual representation. Let's denote it as follows. So it is determined as follows. We take the so if G is an element of our group, so this operator can be denoted as follows. We take the operator which corresponds to inverse element and take the dual operator or conjugate operator.
А почему эта конструкция работает только для конечных групп?
Ну, почему она работает для компактных групп? Тут важно, чтобы представление было конечномерным. Тут не так важно, чтобы группа была конечна, а важно, чтобы представление было конечномерным. Потому что если у вас представление бесконечномерно, но действует в бесконечномерном пространстве, тогда возникает вопрос, а что такое двойственное пространство? Ну, на этот вопрос тоже можно отвечать, но это уже, так сказать, требует некоторых, так сказать, усилий. Можно по-разному понимать. Значит, двойственное пространство к бесконечномерному пространству. Нужна там топология, норма, то уже начинаются некоторые сложности. А для конечномерного пространства там проблем никаких нет.
Спасибо.
Собственно говоря, в этом дело. Well, so it follows what is important for us. So there is a simple connection between the characters of a given representation and the dual. The connection is very simple. So we have that a dual character, meaning the character of a dual representation, is related to the initial character by this relation. This is why, because the conjugation, if we take a basis, then this operation is just transposition, and the trace is not afforded by this operation. So we have this relation. Well, and now let's apply this to our situation. So application to this group. All representations of the symmetry group are self-dual. So for the symmetry group, roughly speaking, there is no difference between representations and dual representations. They are essentially the same. Why? This is because for G symmetry group, G and G inverse are in the same conjugation class. Inversion of permutation does not affect its conjugation class. So essentially there is no difference, and we can pass to dual representation, no problem. We will see why this is important. So this is one operation, and this, in the case of a symmetric group, this operation is trivial. But for other group, it's not trivial. For instance, for the unitary group, which is not finite group map, but compact group, there are representations which are not self-dual. Well, so the next topic I want to discuss is multiplication multiplication by this object. So what I mean, this is the a unique, non-trivial one-dimensional character, which assigns to a permutation its sign, plus minus 1. So given a presentation, you can multiply it, which means that instead of this operator, we take this one, which is plus minus, depending on the sign, the parity of the permutation. And now we have, so one want to understand what this means in terms of our parameterization. So the proposition is follows. Is after multiplication by this. This tensor multiplication is the same because this character, this representation is one-dimensional. It's not even necessary to write these tensors. This is very simple. Just this one. So we get this relation where prime means transposed Young diagram. This is quite natural because we have some natural operation which is an involution, because if we multiply twice by this or by this characters, we return to the initial representation. But what are natural involution in the set of Young diagrams? Quite natural, it's transposition, nothing else. So this is quite natural, but this needs a proof. So this is the proof. The proof of this result. So the idea is as follows. So assume that G and the cycle structure is rho. And then it follows, it's easily seen, that the sign of G is minus 1 to what? N minus L of rho. The length of rho. I assume that G is now the argument is as follows. So this is easy. This is easy to see. This is easy to see. Just write G as a product of cycles, and the parity of a cycle is equal to its length minus 1. And so from this we get this expression. Okay? Now the argument goes as follows. We write according to the Frobenius formula. I recall we have this expression. So we start on this expression and assume that this representation is irreducible, so it corresponds to some yet unknown diagram, lambda tilde, but we want to prove that this diagram is the transposed one. Well, so we can write this is given by this. On the other
Может равняться прямой сумме каких-то p лямбд с индексами.
простите, еще раз.
А почему p лямбда умножить на знаковое представление не может быть равняться какой-то линейной комбинации представлений с разными лямбда с волнами?
Нет, но если у вас представление неприводимо, и вы умножаете его на сигнатурный характер, то оно останется неприводимым, но не может рассыпаться при этом. Значит, оно отвечает какой-то другой диаграмме. Давайте мы обозначим ее через лямбда тильд. То мы покажем, что это лямбда тильд есть просто лямбда транспонирования.
Да, спасибо.
Вот, хорошо. On the other hand, we can write is equal to this expression. So this is equal, I continue. And this is the same. Put this sign inside. So, and apply the involution in the algebra of symmetric function. And we know that proved that, and it follows that this is equal to but we know the involution, the scalar product is invariant under the action of this involution omega. So this is the same.
Почему оно инвариантно?
А потому что мы знаем, как определена эта инволюция, потому что мы знаем, что инволюция вот это мы знаем. И мы знаем, что базис это нормальный. Поэтому инволюция переводит, сохраняет базис как целое. Ну, значит, скалярное произведение инвариантно.
А вы говорили, что омегой надо пользоваться осторожно. Вот в данном случае, почему мы так свободно им пользуемся?
Значит, осторожно.
Ну, то есть оно не всегда существует.
В
Ну,
алгебрических функций оно существует.
функции, хорошо, спасибо.
Оперируем функциями. В пространстве полиномов оно просто не определено. А в пространстве симметрических функций оно определено. Нет проблем. That's all. Yes. Well, so the next topic is the category. It don't want to discuss rigorously what is a category. Just, I want to, this is just a very little formality. So for me is a category finite dimensional vector spaces over complex. Simply, so the expression V is in this category just means the V is a finite dimensional vector space. Very simple. So the objects are the objects of this category are finite dimensional vector spaces over complex numbers, and morphisms objects are finite dimensional vector spaces over C, and morphisms the arrows are linear maps. Between two vector spaces. There is some natural. So first of all, the notation home is the space of linear operators from the space of linear operator from one space to another, and it's itself a vector space. There are some natural operations. Over objects of this category, some natural operations with the vector spaces. Very simple. So what are dualization? If you have a vector space, we can assign it to a dual space, a space of linear functions. And dual to dual is the initial space because all is finite dimensional. Next, we have identification. Identification. If you take the space of linear operators from one space to another, is essentially the same as the tensor product. This is pure linear algebra. Is it clear, or should I explain this point? So just to maybe to make it precise, so if you have, so what is the map? What is the row given a tensor, some decomposable tensor first. Assume this tensor. We assign to it an operator in the space as follows. If you want to apply it to a vector, the result is as follows. V is a vector from this space, and this is the pairing between our space and the due. So in this case, we get a rank 1 operator, and this correspondence extends uniquely by linearity to an isomorphism between this vector space and this vector space. Some other simple examples. We can take a tensor product. Given a vector space, we can take the tensor power number n. Next, we can assign the symmetric power or skew symmetric or exterior. So these are some natural operations over vector spaces. What means natural? This means that each of these operators, each of these operations, say E some operations, is natural because in the sense that given an operator we get morphism so any morphism induces this morphism. In such a situation, we say that F is a functor. So these are examples. These are examples of functors. And I want now our goal is to generalize these examples. What you get, we will get, which is called Schur functors. So my goal now is to explain what are these Schur functors. So it's convenient for me to use a slightly different language. Slightly different language. Instead of representations, let's say modules. So representations of a group G is the same as G module. This is just a terminology, but sometimes it's convenient. So what's practically, what this means? A representation is a pair. Representation and the space of this representation. Sometimes it's convenient to use a single notation. So one can say that H is a G module. Or maybe it's convenient to write pi is a G module, instead of using this duplication representation, one symbol for representation, another symbol for the space, just to unify this. And single object is a vector space with an action of a group, and this means that the space is a G model. Now I need some definition. Which is as follows. So assume that pi is a SN module, so a representation of our symmetric group, and V is a vector space. Then I define another vector space as pi V is a vector space which is defined as follows. By definition, the home from pi to the nth tensor powers. And what this means? So first we remark that this tensor power is n, maybe it's better to say n, s, n module with the action of our symmetric group by permutations tensor factors, which simply means that if G is a permutation, then applying it to a tensor, a decomposable tensor, just means that we have to write as follows. So I would like to emphasize that in order to get a left action on tensors, we need to take the inverse of the permutation. Otherwise, we would get a right action. And if we want to get left action, we need to inverse the permutation. So this is easily seen. So we see that this space is a module of a symmetric group or representation. So we take first the space of all linear operators from this space to this space. And next we take operators which are intertwiners, which commute with the action of a symmetric group. So what we get is some subspace of this home. Not all operators, but only those which commute with the action of a symmetric group. So this is the definition. So this is the same, the space of intertwining operators between these two representations of modules, which is the same. So this is the definition. Now a simple remark that we can get an equivalent definition is as follows. Instead of taking these intertwining operators, we can define this a little bit differently, namely as follows. What does this mean? Instead of taking the space of operators, we can take the tensor product, replace this space by the dual space, and this is the same. We know this was some previous remark. In the space of operator between two spaces, this is V1, this is V2, is the same as the tensor product and taking the dual here. So this is just what I did. But taking into account the intertwining property is equivalent to taking the invariant. So we have an action of a symmetric group here and here, and we take the invariant because the property of being intertwining operators is the same as saying that if you regard an operator from this picture as a vector in this space, the intertwining property is the same as invariance under the action of the symmetric group. But next, because we know that in the symmetric group case, the dualization does nothing, so this is the same as simply writing pi. So we take the tensor product of two representations. One is pi, another is this tensor representation with the action of the group by permutations. And next we take invariant elements. So is it clear, or some questions maybe? This is because...
Можете еще раз сказать, почему брали дуализацию у Пи?
Сейчас скажу, да. Потому что у нас общий принцип. Сначала, если мы ничего не знаем, у нас есть общий принцип, что пространство операторов, я его повторяю, из одного пространства в другое, это то же самое, что тензорное. Я писал здесь звездочкой, я немножко ставлю, здесь вместо делаю. Вот мы это знаем. Так? Поэтому формально мы, когда у нас V1 это π, это π, да, мы должны поставить значок двойственного пространства. Вот, собственно, о чем идет речь.
Почему его убрали потом?
А потому что это то же самое представление в случае симметрической группы.
Понятно, спасибо.
Могли бы делать такого рода вещи и в какой-то другой ситуации. Там это было бы существенно. А здесь мы это уже знаем, я это уже говорю, что эта операция ничего не меняет. Поэтому мы можем заменить и с равным успехом писать вот так. Можем писать. Вот. И это то же самое, что исходное определение. Исходное определение, как если мы возьмем клон. К чему я это все веду? Сейчас вы увидите. Now I can define what is definition. operators. Is it as follows? So given if lambda is a Young diagram of n boxes, and pi sub lambda is the corresponding representation, irreducible representation, and we just write simply write instead of writing this, we just write this. And this is a sure functor with label or index. So what I did, I said that for any vector space in any Young diagram, given these two objects, this and this, we can assign in some natural way another vector space, which is denoted as follows. It can be defined in two equivalent ways, as a home, as a space of intertwining operators, of certain intertwining operators, or as a subspace of Sn invariance in some tensor product, which is essentially the same. This is some natural operation. It is a functor in the sense that given a map morphism from two spaces, which induces a map, linear map, such a type. Yeah. So some little remark. So some examples. So it's what happens in particular cases. One row diagram. Then is the trivial one-dimensional presentation, which corresponds to such a diagram with n boxes. And what is this? Simply the symmetric power. This is easily seen from the very definition. And next, what happens if lambda is one column diagram, which is the sign character. One column Young diagram. Then we can guess then this object is the exterior power. Note, if n is greater than the dimension of V, then this object is zero, or the very large exterior power is zero. So this shows that in principle, this space can be zero, which is not surprising, because some subspace of intertwiners can be zero. No non-trivial intertwining operators, or no non-zero invariant vectors. So this may happen.
Можно спросить?
Да, пожалуйста, конечно.
Почему это равно внешней степени n?
Ну, просто определение. Просто если вы немножко подумаете, примените определение, капельку подумайте, вы увидите, что то же самое. То есть исходное определение.
Хорошо.
Вы увидите, что это так. Now what I want to discuss with sure wire duality. Of convenience. I want to discuss what this means. Well, let's fix X vector space. A simple one can assume that this is a coordinate vector space of dimension equal to capital N. And we have, no, I'm sorry. Let's forget for some, I need some preparation. Some preparation. What I want. So assume, let's start from some very general situation. So G is a finite group, arbitrary finite group, and this is the set of its irreducible representations, which some pi's. And let X, another representation, let me say a G module, which is the same, and take the isotypic decomposition. Isotypic decomposition of X. We simply decompose it into irreducible representations and group together equivalent irreducible components. So we can write this is as follows. Write it as a direct sum, formally of all irreducibles, and some direct sum, some multiplicity. Let's denote this multiplicity. It can be 0, which means that a given pi does not enter into this decomposition of X. And rewrite this. This is formally, it's convenient to rewrite it as follows. The direct sum of the pi's of irreducibles of what? We take the tensor products and the vector space of this dimension. If the multiplicity is 0, this just means that this sum actually disappears from the picture. So this is some auxiliary vector space. So this picture looks a little bit artificial because what we did, instead of taking some number of copies of this pi, we just represent this vector space, a direct sum, some m-fold direct sum, as a tensor product. This is some auxiliary vector space. But we want to determine this artificial, in a sense, object in a more canonical way. And this can be done. We just identify this artificial object with what? With the space of intertwining operators between pi and x. Why it's legitimate? Because the dimension of the space of intertwining operators between a given irreducible pi and our initial representation is exactly the multiplicity of pi in this decomposition. So this space can be identified with this. And this is some canonical object, which depends only on pi and x and nothing else. Some canonical objects. So this gives us a map, and this gives us a mean to make this artificial vector space some canonical object, turn it into some canonical object. This one. Okay. So now we can write. Now we can write. In our isotypic decomposition, we can write in some canonical way the direct sum over the due of this object. So this is isotypic decomposition written in some canonical way, to write it. I repeat again that it may happen in principle that for certain pi, this space is zero, and so this summand is actually missing. Okay. And this is the same, and this can also be written as follows. This is the same space, but written in a little bit different way. For the symmetric group, it's the same, because we know that this and this, we can replace what I want to say. We can replace a dual representation by initial pi, but for in some general setting, this can be something different from pi. But now apply this. Now apply this. I'm in this picture. Like this. To our special case. We take G is the symmetric group. Pi is pi lambda. X is with the permutation action of the symmetric group. And V is, one can assume it is a coordinate vector space. So what we get now?
А вы там написали лямбда принадлежит Sn?
Да, это нехорошо. Спасибо. Так писать нельзя. Спасибо. Конечно. Спасибо.
Извините, а вот в формуле в красной рамочке, вот если home расписать, то мы должны написать, ну, если круглую скобку расписать, то будет π умножить тензор на π со звездочкой умножить на x. А дальше куда оно пропало? Как будто кажется, что какой-то π пропало. Или почему x перешло просто в home?
Где x перешел в home? Почему это то же самое, что это?
Ну, да.
Ну, это же это все время я говорю одно и то же. Я же уже эту формулу писал, что вот это то же самое, что вот это.
Ну, раньше у нас было v тензор на n вместо home, и оно оставалось при переходе
Ну, у
уже.
нас раньше было конкретно вот это. И сейчас снова x будет вот этим пространством. Я же писал, что у нас есть, когда у нас есть home v1, v2, это то же самое, что v1 со звездочкой на тензор v2.
Вот, а это еще умножается на π.
Где он?
Да, вот
π со звездочкой на x еще умножается на π при этом. Тензор. Если мы расписываем.
Сейчас. Да, вы правы. Да. Да, извините, да. Вы меня поймали, правильно поймали. Спасибо большое. Да, это вранье. Спасибо, да, конечно, вы правы. Вы абсолютно правы. Я заврался. Я заврался. Спасибо большое. Да. Конечно. Вот так. О, спасибо. Это было вранье. Конечно, мне нужно вот это пространство отождествить с этим, а это π здесь остается, оно никуда не денется. Это вот вспомогательное вот это пространство кратности. Давайте даже я скажу. Это стоит даже так сказать. Multiplicity space. Пространство кратности вот нашего этого π. Сколько раз оно входит? Может быть, нулевая кратность, может еще какая-то. Вот это пространство кратности, оно материализуется вот либо вот так, либо вот так. Да, вы правы. Вот. Теперь, now we apply this to our concrete situation. And we can write direct sum and what is the space? And this is exactly our Schur function, Schur functor, y to the. Yeah. So this is our multiplicity space. Multiplicity space corresponding to. Well, what now? The next observation is a GL module. We have, so this is the group of invertible linear operators on our space. And we have a natural action of this group. It's not a finite group. But nevertheless, there is an action of it, which is its action. Its action on the tensor space is diagonal, which means that if A is some linear operator, then its action on the tensor is defined component-wise. And what is essentially important? The action of this group on space commutes with the action of the symmetric. Which means that if we apply first an operator to a tensor and then permute the factors according to a permutation of indices, or vice versa, we first permute and next apply this. This is the same. So this means that we have follows. We get a bimodal structure on this tensor space, or else an action or permute representation, linear action or representation of the product group, the symmetry group times this group, which is the same symmetry group times the general linear group, if we identify V with the coordinate space. And the corollary this space is always a G L V mod. From the very definition, as a home space, so I recall this. The definition is the home of the symmetry group. So we take intertwining operators over this group, but because the action inside V commutes with this action, it's a group of symmetry of all this picture, of all the structure allows symmetries induced by the action of a general linear group inside V. So this produces an action of this group on the whole this space. So this space becomes a GLV module. An action, linear action. So this is a representation. This space becomes the space of a certain representation of this group. So well, and moreover, is the decomposition that I wrote Let me write it again. Just this way. This is a decomposition of these modules by modules. So we have initially we have an action of this product group in this space, and we see that it can be decomposed into certain sub-representations, each of which can be represented as a tensor product of a representation of one group, and another tensor factor is a representation of this group. So we take this picture. And now I want to relate this picture with the Frobenius formula. Now relate this with Frobenius formula, which says, I recall, that we have this picture. More precisely, I want to write it in a little bit different way. I want to pass to finitely many variables. Namely, I want to write as follows. I want to write this as follows. And now I want to explain why this picture is the materialization of this combinatorial formula. This is a decomposition of some vector space, and this is some equality between symmetric polynomials. And I want to relate term by term, this to this, this to this, and this to this. How to do? In order to do this, we have to pass to characters. So, compute characters and traces of operators. So we have an action of operators which corresponds to the elements of this product group. So we take G permutation, A, an operator, a matrix from G and V, and compute the trace of GA on this space in two ways. So assume that A has eigenvalues, some eigenvalues, and G has a cycle structure corresponding to some partition rho. So I claim the trace of the operator corresponding to this in this space is given by this expression, which relate this quantity to the trace of a certain operator on this space, namely to the trace of the operator which corresponds to such a pair with G of type rho and A has eigenvalues. This one. Okay. So this is very simple to see. Very simple to see. So the proof is as follows. So we may assume that A is simply the diagonal matrix. Why? This is because a typical complex matrix can be diagonalized. And because this quantity as a function of A is continuous, it suffices to consider the non-degenerate case when A is semi-simple matrix, so it can be put into a diagonal form. The trace does not depend on the it does not change under conjugation, and so we may assume that it's simply diagonal matrix. And we may also assume that G takes some specific form. So G is one cycle of length ρ1. The next cycle starts from the next value and till this one.
А почему эти циклы не пересекаются?
Не могут пересечься. Эти первые числа, первые ρ1 чисел, потом следующие ρ2 чисел и так далее. Как они могут пересечься?
То есть, имеется в виду следующие скобки, первое число, которое начинается, почему не может быть меньше, чем ρ1, например?
Мы берем первые ρ1 чисел, потом следующие ρ2 чисел. Как они могут пересечься?
А почему это ситуация общего положения?
Подождите, здесь нет никакого общего положения. Я уже перешел к симметрической группе. Про общее положение я говорил, когда мы имели дело с матрицами, а здесь я перешел к симметрической группе.
Хорошо, спасибо.
Симметрическая, просто перестановка. Мы записываем, если у нас задана какая-то цикловая структура, мы записываем ее в таком виде, что ρ1, цикл длины ρ1, следующий цикл длины ρ2, и мы выписываем вот эти числа натуральные просто в естественном порядке. Понятно ли это? Это длина последнего цикла. К – это длина разбиения. Теперь мы считаем. Now we compute we compute trace in this vector space. This operator, we can write this in any order, first A and next G, or first G, next A, because we commute in the basis. In the basis. The tensor is the standard. This. How to compute the trace in this situation? We just should take the diagonal values of our operator. What is the action of A? The action of A, because A is diagonal, any such vector is multiplied by some quantity. And what is the action of G? Of this is some permutations. If we want that the basis element remains the same up to some factor, some number of factors, so the contribution to trace is non-zero only if we have these indices. The first row one indices are the same. The next indices are also the same. Okay. And from this picture, this contribution, the contribution is this one. And so on. So this is the trace. Just expand this quantity, and we just get the trace. Okay, so this is a little... Я прошу прощения, я уже превысил свое время, но давайте я уже закончу. Просто легкое упражнение, увидеть, что след действительно равен вот этому. Давайте я буду считать, что я доказал эту левую. Сегодня это упражнение. Так. Значит, мы получили уже, что след вот в этом пространстве, the trace in this space is equal to this. The trace in this space is this quantity. Okay. And because this matrix is non-degenerate, we conclude that the trace of A on this space must be equal to this one. Okay? So we conclude trace A, this space should be equal to this quantity. So what is the corollary? corollary. This space is zero if and only if the length of lambda is greater than n, because it's just a condition for this Schur polynomial to be zero. So we see, as a consequence of this computation, we see that in this decomposition, it may happen that this Schur functor gives us zero. This happens if a number of boxes n is greater than the dimension of a space. So if small n is bigger than the capital N, this object is equal to zero, which agrees with the fact if lambda is one column Young diagram and small n is greater than capital N, and the exterior power is zero. This is a generalization of this fact. And a final remark, is also that this space when non-zero, which means that capital N should be large enough as compared with the length of lambda, is an irreducible representation of G. For this one needs some information about the representation theory of GLN. One knows that if the character of a representation of GLN is given by the Schur function, which just means that the representation is irreducible, which requires some information about representation theory of GLN. So what I would like to finally say that this is exactly the decomposition of this space into irreducible representations of this group. And these irreducible representations are of very specific form. They are tensor product of two irreducible representations of one group and the other group, which is not surprising. But what is non-evident, there is some natural parametrization of representations of this group by Young diagrams, and also some parametrization of certain representations of this group, also by Young diagrams. And the labels are the same here as here. And this is called the Schur-Weil duality, which connects representations of this group and this group. This is a fundamental result which has a lot of consequences, a lot of generalizations, extensions, variations, and so on. So, well, I have to stop this moment. Let me switch off.